Hey everyone, welcome back to the channel. Let me just check if we are live. Yes, we are. So today we will be solving another problem from our SD sheet, and we are going to solve coin piles. Okay. So first let's understand this problem statement. What does it say? This is a good question actually. Just give me a second. Okay, so you are given, understand the question first, you are given n piles of coins, each containing ai, each containing number of coins. Okay, find minimum number of coins to be removed such that the absolute difference of coins in any two piles is at most k. Note, you can also remove a pile by removing all the coins of that pile. Let's understand one test case, then we will see what we have to do in this question. Let me just write this test case. Okay, have a look. So for example, we have a pile of coins as 1, 5, 1, okay, 2, 5 and 1. This is the coins we are given. These are the piles of coins. Okay, one coin, in another pile I have 5, okay, like this, so on and so forth. Now so the thing here is that you have to remove minimum coins. What is the minimum number of coins that you can remove such that the maximum difference in any two piles is 3? It does not exceed more than 3. So if you try to understand, this is pile 1. So other pile has how many coins? 1, 2, 3, 4 and 5. Fine. Then this pile has only 1. Other pile has 2 coins. Then we have 5 again. Let me just 3, 4 and 5. Okay. And then we have again 1 coin. So what you need to understand here is that if you see do you find any pile whose difference is exceeding this quantity, which is 3? If I see the difference of these two piles, I can clearly see that the difference is definitely greater than 3. These are the coins that are extra and this count is 4. If I check for this and this pile, I can see that their difference is exactly 0, which is less than this value. So these piles are good, but this pile and this pile is also not good as per our condition. Why? Because the maximum difference can be 3. Here also it is going to create some problem. If I check about this pile with this and this pile, okay, these are in good state. That means they are following the condition that the maximum difference of the piles can be 3 and not more than that. So the problem that we have is due to this pile and this pile. If I remove coins from these two piles, can I remove the quantity of coins in such a way that the maximum difference comes out to be 3 if I compare it with any pile present? Okay, so let's try. If I remove one coin from here, what will be the difference? 4 minus 1, 3. Okay, that will work for everyone. If I see if it works with the minimum, the pile which has minimum coin. So try to understand. I am right now just helping you understand the question with the very brute force approach. So what I saw here is that I see that this pile comes out to be the pile with the maximum number of coins. Okay, the quantity of coins that I remove from it, if that follows the condition that we have to follow, right, that maximum difference can be 3. If this holds true with the pile having minimum number of coins, that means I am in a good state. The number of coins that I have removed can work for the other pile with maximum coins also. Understanding my point? Once I can verify that if I remove just one coin from here, I know this difference is good to follow the condition, that is now the difference between the pile having minimum coins and the pile from which I just removed is equal to 3. So I do not have to worry about the other piles which are having coins more than this one. For example, if I compare it with 2, now the difference between these two piles is 4. Total number of coins here 4 minus 2, 2. Anyway, that difference is going to come under this value only, right? So the intent here was that if somehow, this is the brute force approach again, I am repeating, if somehow, let's say I sort this array. If I sort this array, what am I going to get? You'll see 1. How many ones are there? 3 ones. then I have 1 2 and 2 5s. This is the sorted array, that sorted form of this array, right? So if I can see that the maximum ones, okay, maximum piles will be in this side. If I see, okay, which is causing me trouble, I see 2 is also good, 1 1 1 also good. If I, let's say, keep 2 pointers, okay, one in the right hand side and one in the left hand side, I see that the maximum minus minimum, 5 minus 1 is 4. I want this difference to be 3. So let's do one thing. Let's remove the ideal number of coins here. Maximum number of coins I can have here is 4. So what is the difference? What I can do is 5 minus 1. Okay. This is some quantity. 5 minus 1 is 4. What I actually, how many coins I want to remove will be given by when I subtract the maximum difference that is allowed to have. Okay. I just remove that value from this value, I'll get 1. Okay, so the coin that I have removed so far is 1 from here. Okay, then I move my right pointer to this position, and let's say left is still here. Now if I check, okay, 5, again same thing, I'll subtract this ARR right minus ARR left, 4. I'll get minus, what is the maximum difference allowed? 3. That means I will remove 1 coin from here also. That is also okay. So 1 coin is removed from here. Now I move my right pointer here. I check the difference. I see the difference is less than 3 only anyway. So I don't need to do any more removals, right? So I got 2 coins anyway. But for this test case, this approach worked. Why will it fail and where will it fail is, if you see, the question says that you can remove, in order to minimize the number of coins that you are removing, you can also remove a pile by removing all the coins of that pile. So for example, I have a test case like this. Have a look. Let's say I have 3, okay, 10, and what is, let's say 12, 15, okay, and again your K is 3. So the maximum difference between any two piles can be maximum 3 and not more than that. I will see that here I have already written it in sorted order. Let's come at this index. I see this pile has 10 coins. In order to satisfy this condition, how many maximum coins I can have? If I check this pile, it has 3. At max, any pile, if I want to measure it using this pile as a reference, at max any pile can have 3 plus 3, 6 coins. Getting my point? So any pile having greater than 6 coins means I will have to remove coins from that. So in order to satisfy this condition, how many coins will I need to remove from this pile? So at max, this 10 can be 6. Okay, so to make it 6, I will have to remove 10 minus 6 equal to 4 coins from this pile. Okay, so if I remove 4 coins from this pile, same thing, at max, what is allowed? At max I can have 6 if I'm keeping this pile as my reference. Getting my point? So in order to make this pile have 6 coins, I will have to remove 12 minus 6 equal to 6 coins from here also, and these will keep adding up. 4 plus 6, total 10 coins I have removed so far. So from here 6 I have removed. Now to make this pile equivalent to 6 coins, I will have to remove 15 minus 6 equal to 9 coins, right? So 9 from here. So 6 plus 4, 10 plus 9. I have removed 19 coins to satisfy this condition. But you'll see this is not the minimum value. If I tell you the answer for this test case, this is just, I have just randomly created, but this is not the right answer. We can minimize the value of these coins that I have just removed. How? By simply removing this whole pile of coins. This whole pile contains 3 coins. Why not remove this pile? Now I am left with 10, 12 and 15. You will see at max, no, not only just 3, I removed 3. Plus what I can do is, if I take 10 as a reference, 12 satisfies the condition. 15 will say that 15 minus 10 is what? 5. The difference here exceeds 3. So why not remove some coins from here? How many coins should I remove? So what is allowed value? 10 and add 3 to it. So 13 is what ideally should be present here. So what is the difference? 15 minus 13 is 2. So I'll add 2 here, right? So this is case by case. I've just shown you case by case how we are handling. So here the minimum possible coins that I can remove in order to satisfy this condition is 5. So you see from 19 we came to 5, right? Now what is the approach that will work for every test case? We are already through the solution, we are already through our logic. Let's understand the approach that will work for every test case. Let me just see if you guys have any doubts so far. Guys, you can write your doubts in the chat section. We came to, and let me know if the voice is clear or not. Okay, fine. Now let's see, using this example only, what was it? 111 255. Let's take this 111 255. So one thing you have understood, that we are, and case 3, we are taking 1 as reference. Okay, one by one, what we are going to do, we are going to take each pile as a reference pile, and we will check what is the maximum possible coins that is allowed in the other piles. How are we going to do that? Let's understand. So I told you for here the answer is very straightforward, that is 2. But what we are going to do here is that, let's say right now I am at this index, right? According to this index, according to this pile, what is the maximum number of coins I can have in any pile? So allowed coins in any pile, if I consider this as reference, is 4, right? So I should not have any pile having coins greater than 4. So what will I do? I will go ahead and check how many piles I have who are having coins greater than 4. So I'll iterate, I'll see that these are the 2 piles having. Once I have only one pile, the next further piles till n-1th index are going to be greater or equal to that. So I just need to know the first index at which the number of coins is just greater than 4. Basically, I will find the upper bound of A of I, right? Once I know that, I can know how many coins I need to remove. So if I'm at this index, right? If I'm at this index, first thing is that I'll not start from here. I'll start from second index, that is index 1. Why? You'll understand why. Because what I'll be trying to do here is, we are trying to see how many minimum coins I can remove. Okay, so I am considering, if I am starting from this index, just have a look at the diagram and then you will understand. I am right now at this index. I found that 5 is the one having this value greater than 4. So what I need to do, I need to know what are the number of, how many coins I have who need to be reduced, how many piles I have who need to be reduced. So once I find this index, right, IDX, let's say here is, this is the index which is having coins greater than this value. So do I need to traverse through all the coins and subtract how many coins I need to remove to make it 4? That is the current value minus what is the maximum allowed value. 5 minus 4, that is equal to 1. So 1 from here plus again 1 from here. So why traverse over all the corresponding piles after this index? Let's do one thing. Once I know the index, this is a sorted array. Let's see how many more such piles are there. So n minus 1, right? This is 0, 1, 2, 3, 4, 5. This is index 5. So n minus 1 is 5. 5 minus this index, IDX, right? Do IDX minus 1. Okay, IDX minus 1. So what is your n? N minus 1 is 0, 1, 2, 3, 4, 5. So basically 5 minus 3 is what I'm doing, right? This is giving me the number of piles having coins greater than 4. So this, I got this. I just need to multiply this value with the number of coins that is allowed. Try to understand what I'm saying. See, we'll just form a formula here. What I wanted to do was, I need to know what are the total number of coins I have currently. So that is 10 number of coins that I currently have. What I need to reduce is how many indexes are there having coins greater than 4. These are 2, right? So you'll just multiply this with the total allowed coins, that is 4. So these are the number of coins that you're removing. This is the total coins whose total coins which are present in the piles having coins greater than 4. So these are these coins, right? 10. Now you are reducing this value to know how many coins you are removing, because this is the total allowed coins. If condition was being followed, ideally it should have been 4 and it should have been 4 also, so that k, the maximum difference between this pile and these piles, remains at max 3. So allowed was 8. So I just did nothing. I just multiplied how many such positions are there, 2 such piles are there, multiplied by the allowed coins, that, and I just subtracted from here so that I can know this is the coins that I need to remove. So I got 2 from here. Try to understand. I got 2 from here. Okay. Now I'll do what? I'll just go ahead and check. Do I need to do this process again when I see that I have done this process for 1 already? Now if the next index value is also equal to the previous index, I will ignore and move ahead. Why? Because I simply wanted to know how many such piles are there and how many coins I need to remove, which I have done already for that corresponding a of I. Right? I'll just move to the new value, which is 2. For 2, I'll repeat the same process. What first is, you find the upper bound of 2. How will you find this upper bound of 2? A of I. That you will find that what is the maximum possible coins allowed if you are taking 2 as your reference. Right now your index is 2. So 2 plus allowed maximum coins that you can have in any other pile can be 5. So that the difference of pile having 5 coins and the pile having 2 coins does not exceed k, right? So allowed possible value is 5. I see that. Now I'll find the upper bound. I'll get upper bound function will return me -1. Why? Because I do not have any pile of coins having coins greater than 5, so that this value would not satisfy, right? So I will not have any such pile. It will return me -1. I know that I do not have to remove any other coin. So that is all about it. You will just simply repeat this process for all the coins till the last index. And what you need to do, you need to keep a check. If you are finding duplicate value, ignore and move ahead, right? The other thing that you need to understand, how are we finding upper bound? That is also very simple. You can simply use binary search. In my binary search, let's say your start index is this, right? And your end index is this, for example, and a of I, what you're passing is 1, right? You're passing 1 as your a of I. You just have to find its upper bound. So what will be the middle value? You'll find 2. Right now you see that 2 is greater than the value that you have passed, 1. If 2 is greater than 1, as of now, I'm just using binary search here. So this question is more towards you to understand. Code is not going to be difficult again. Just try to understand. I am passing 1 1. What is it? 1 1 1 2 5 5. I am just applying a binary search in order to get my upper. For example, my index is here. So a of I that I'm passing is 1. I just need to find the upper bound of 1. Upper bound of 1 here can be what? So basically I need to know that index which is having coins which holds false for the condition that we want. The condition is that maximum allowed coins is 4. So any pile of coin having value greater than 4. So what you will reference that you will pass is 1 plus the coins that are allowed. So 1 plus 3 is 4. So basically you have to find the upper bound of 4. If your index is at this position, if your I currently, try to understand what we are doing. If your I currently is at this position, you will pass 4 as the reference to your upper bound function to know that which value is just greater than 4. Ideally you will get this answer, but how, we'll see. So for example, your left index is this, your right index is this. What you are checking, which value is greater than 4, right? You have to find this thing. So the middle value that you find is 2. 2 is not greater than 4. So that means you will find a bigger value in the right of this 2. So your left from here moves to this value. Now your left is pointing to 5, right is pointing to 5, and mid will also point to 5 only. You will see that 5 is greater than 4. So right now ARR of this thing, or you can say the answer, you will update your answer at equal to ARR of mid, which is 5. Answer will point to 5. Now you will you already found this value. You will do one thing. You will move your right pointer to this ARR of mid -1. So basically it will surpass this left index, you know that this is the maximum. Simple binary search. I'm not going into details of binary search, just wanted to show you how are we going to do this thing. How are we, upper bound function, I'm assuming you already know how do we find it. So this is what we are doing next. Okay, now I found this answer 5, and then we are going to make use of this formula that we just discovered, that how are we going to solve. The logic behind this is, what is the number of coins I'll have to remove from all the values from this index till the last index, and this index I will get from my upper bound function. Okay, so that can be done. One more thing, one extra thing, since I will also have to remove the coins from the preceding values of the index. See, for example, when I was present at this index, I found the upper bound and I found that 2 coins were removed from here to get the condition satisfied. One from here, one from here, right? So 2 were already removed, but you need to understand. For I think I'll have to take another good example to make you understand what we're trying to do. I will also have to remove, let's say 1 2 6 6. So guys, what I'm trying to tell you, for example, I'm sitting at this index. Okay, I just found the upper bound, k is again equal to 3. So allowed maximum coins for this case, if I'm present at this index, is 5 in any pile, and I'll see that this is the upper bound. So what you need to see here is that I already removed 1 coin from here, 1 coin from here, I made them 5, so 2 coins were removed. But also you need to understand, since you are sitting at this index, the preceding values are anyway going to fail your condition that maximum difference should be 3, so you'll have to remove this whole pile also. Okay, so this whole pile containing 1 coin is also removed. So simultaneously you will be adding these I minus 1th, all the coins till if this is your ith index coin, all the coins till I minus 1th index, they will also be added to the number of coins I have removed. So for that we are going to use prefix sum. Prefix sum will help us, at least when I know the index is I can simply do what? If P of I is the sum of all the coins till ith index, so P of I minus 1 will give me sum of all the coins till I minus 1th index. I will add that, and then I will do my task of finding upper bound, and using that formula I'll get the coins and I will add it. Okay, so you will see what formula that turns out to be, and we will understand. Got it? Okay, so that's what we are going to basically do. And so this is all about this question. Let me know if you have any doubts. I'll just simply check if you guys have any doubts. Just checking. Okay, so someone is asking why you are starting from I minus 1, I equal to 1. So that is for the only for the cases where you find duplicates. For example, 1 1 2 6 6. Anyway, I am starting from, if you think that we are starting from I equal to 1 index, no, that is not true. We are anyway starting from I equal to 0. Just to make it a little short, I just explained for that particular test case. When I will start from I equal to 0, I will make this as reference and repeat and do the same process that I explained you for I equal to 1th index. Just that when I will be at this index, I will put a condition. If A of I is equal to A of I minus 1, then I will skip and move to the other part. Anyway, don't worry, we are going to start from I equal to 0th index only. Okay, we are going to make every coin as a reference, as long as it's not the duplicate. Check, I will get some number of coins from each case, and every time I'll find the minimum as I'm iterating over this array, and I will check what is the number of coins I have to remove for each cases, and I'll keep finding the minimum of the I'll keep tracking what is the minimum so far, and finally I'll return that minimum value. Okay, I hope your doubt is clear. Now whatever we discussed, let's see it once it in code what we have done here. Okay, so this was the function that we wanted to complete. This is your array, this is your length of array, and this is the k, that is the maximum possible difference you can have between any two piles. First thing, we sorted the array, right? We just created a new array. Why? You will see. Starting from this is just an array to keep the prefix sum, right? Why? As I told you, if I have the prefix sum already, it will help me do my task without having to reiterate over the array. For example, if I have an array like this 1, I'm just doing the prefix sum 1 plus 2 3, 3 plus 6 9, 9 plus 6 15. So once I have this, it will get easier for me to evaluate what all things we just discussed. Fine. So this is filling up your prefix array. Fine. Now let's iterate over our original array. We have just kept this prefix array for our calculations. We are not going to do anything else. We are not going to operate over the prefix sum array. Now this is the answer which we will return, which will contain the minimum number of coins that we just removed. So I am initializing it with the maximum value, so that on comparison I'll get the minimum ones starting from 0th index. Okay, now see what we are doing. We are iterating over our array starting from 0th index. This index will return you what is that first pile of coin whose value is greater than that ai plus k coins. Understood? And for that we have written this find upper function. Just assume that right now this function will return me that index at which I am finding ai plus k coins greater than ai plus k. So see, the target that I am passing here is, this is the target. I just have to find an upper bound of it. This is what we exactly discussed. For example, if you are sitting at 1, you will see 1 plus 3 is 4. What are the piles of coins having value greater than 4? So the first index that will be having this value will be returned. So basically upper bound function will return the index of this value. Okay, so target that I am passing is, it's not a of I, it's a of I plus k. I am stressing on this point again. I have already told this thing. Now I am assuming you understand why we are passing it. Start is the ith index, right, at which you are present. That will be your Windows start, and n minus 1 is the right index, that will be the end index. Fine. Simple binary search like we do, not going into it. Finally you'll get the index of it. Once I get my index, the next task is, you will check if index is equal to -1. That means all the piles of coins are satisfying the condition from that ith index, right? Starting from that ith index, I do not have any pile of coin which is not satisfying the condition. So you'll do nothing. You'll just make your index point to n. Then if your index is not equal to -1, this condition I have put to check if you have duplicates. So if you have duplicates, you are checking this condition, your start will point to prefix of I minus 1. This is simply that. Why? Because if you found a duplicate, this prefix of I minus 1 is the prefix sum. Try to understand, this is the prefix sum. Okay, this is just an extra condition we have added for that duplicate thing. Otherwise, in all the cases, what we are doing, this is the main formula which is helping us find the minimum number of coins. Math.min answer, which I have initialized with max value. This is what this start is p of I minus 1 in case we have a duplicate. If not, we have already initialized our start with 0. Okay, so p of this start is the number of coins I am having before that ith index pile. I told you if I am at this position I equal to 1, I have to remove these coins also. If I am at this index, for example, then what is the sum of coins that I'll have to remove? That will be a of 0 plus a of 1. So that will be given to us by p of 1. P of 1 will give me sum of all the coins from 0th index till 1 index. That is why we are writing it in this way. So this will be given to us by start, plus this is the formula, means not formula, this is the calculations what we are doing. P of n minus 1 is the sum of all the values in your array till n minus 1th index. P of ind minus 1 is giving you the sum of all the values till ind index, right? The coins till ind minus 1 right? This is the sum of piles of coins which are greater than the allowed number of coins. Just understand it in this way. Already discussed, you'll have to reiterate and then you will understand. For example, we were here, right? So this will give you these number of coins. Basically, P of n minus 1 is total sum. Okay, so if somehow you know this is your index IND, so P of IND minus 1 will give you sum of all the coins till here. So if you subtract from here till here, you'll get the count of coins you have till here in this window. Just that, this is what we are doing, right? Minus what we are doing now, you have to find how many coins you have to remove. This is A of I plus K, this is the number of coins allowed, and this is the number of coins that is allowed, right? For example, A of I is 1 and allowed K is 3, so 4 is what you are allowed. So how many times you'll have to multiply? As many number of piles you have. So here you have 2. So basically 10 is the number of coins you have. 10 will be calculated by this value, 10 will be calculated by this, and this will calculate the allowed number of coins, that is 2 into, these are 2 piles, 2 into possible allowed values was 4. So total 8 was allowed and I have 10. So how many coins you will remove? 10 minus 8, 2. This is what they are giving you. I hope you have understood, right? So it will evaluate the minimum of that, and you'll keep repeating this process until you reach the last value of your array. That's what you are going to do. Okay, so that is all about this problem, guys. Let me know if you have any doubts. If not, we will wrap this lecture. Okay, so that's all. Fine then, if you have no doubts, we'll wrap it up and see you all in the next lecture tomorrow. Bye bye and take care, everyone. Thank you, Dayashankar.